Okay, then like I'll start sharing my screen. I hope it's visible to you. Can someone confirm? Probably in the chat.
Yes, visible.
Okay, okay. So basically, like this is the NPTEL CS52 reinforcement learning course by Professor Palaraman Ravindran of CSE Department IT Madras, and I'm Sandarbh Yadav from Computer Science Department of IIT Bombay, and I am a PMRF TA for this session. So basically, like this is the week 3. So every week, like we conduct a session for 2 hours, and it's like 12 weeks for the entire course. Then it becomes 24 hours, and there will be 1 hour session just before your exams. So it becomes 25 hours per semester. So it's like this is the requirement of PMRF. Like we are required to do 25 hours of TA work in a semester. So again, like some of you may be new, so I'll reiterate these again. So this session like happens on Tuesdays, 6 p.m. to 8 p.m. So there are basically like 3 sessions going on parallelly. One is on Saturdays, I think. Second is on Monday, and this one is on Tuesdays. And the same link, and anyone who has taken this course can attend. Like the main reason to attend is like there will be discussions on practice assignments also and assignments, and there will be extra problem solving like apart from these two, and you can clear your doubts. And the main reason is two-way communication, right? Like in like the general course, like you have been given recorded videos, so like you don't get the chance to interact one-on-one. So these sessions provide that opportunity, and the expectation again is that you should have at least watched the weekly lecture. So we are on week 3, so by this time you should have definitely watched the lectures till week 3, and at least made an attempt to solve the weekly assignments and practice assignment. Although you might not have got the correct answer, but at least you should have tried once. And it is recommended to read the Sutton and Bartow book. This is basically called the Bible of reinforcement learning. So this is from the same authors who have like kind of popularized reinforcement learning a lot. So this is like the main book of reinforcement learning. And obviously, like I will be sharing these slides and recordings, but don't rely on them too much because like the deadline for assignments from now on like is like Wednesday, and this session is on Tuesday, right? So like we share it on Tuesday, but it might reach you by Wednesday or maybe Wednesday noon, because YouTube itself like takes up a lot of time for pre-processing these videos, and then like we need to update the demos and all. So general guidelines are like try to keep yourself muted. And if there is some doubt, you can either unmute yourself and ask or just ask in chat, and try to be responsive, and try to solve the problem simultaneously. And if time is needed, then I'll be giving time to you. And we will be following the following order. Like this is same as usual. So practice assignment first, then some problem solving. Then I'll be showing demo. Like so today there will be two demos. One is for Thompson sampling. Basically both are for Thompson sampling, but the on two problems, and assignment at the last. So audience interaction now, like I think like someone is new here. Uh, maybe like Aryan, I think you are new, and whoever is new, like whoever is attending this session for the first time, kindly introduce yourself. Like what is your background, like bachelor's or master's, and from which college, so that I get an idea of the audience.
Hello, everyone. I am
Yeah,
Aryan.
right,
Uh, I am currently pursuing BTech in Information Technology from PDU. I'm in
right.
third year.
Okay.
Yes.
Is there anyone else who is new? I think
Hello
Harshit.
everyone, I am Nil
Yeah,
Shah. I am
right.
pursuing BTech in AIML from Charusat University, Gujarat.
Right. Okay, got it. So basically, more of bachelor's students. Okay, then we move to the topics. So the topics which were covered in week 3 were policy search, then reinforced algorithm, then contextual bandits. So till this part, like it was bandits. Now whatever comes after this is full RL. So full RL was introduced first, and then like it was discussed returns, value functions, and some brief discussion on MDPs. Like this will continue in the next week also. So let's move to the practice assignment 3. So, like in full RL problem, which of the following is determined by the agent? Like, so what happens in RL? There is an environment and there is an agent, right? Agent takes action on this environment and environment comes up with state and reward. And this loop keeps on happening again and again over time. So basically, like the environment has control over state and reward, and agent has control only on the action. So agent control, it cannot control the state, right? It is given by the environment. It cannot control reward also because it is also decided by the given by the environment. And it definitely has control over action. And this control it exerts through a policy pi in which it learns a mapping from like state to action side, or it could be even probability distribution over action side. So if this happens, then it's deterministic policy, otherwise it's stochastic policy. So I hope like there is no doubt in this question, right? Okay, then I'll move to the second question. Which of the following statement is true about the RL problem? Our main aim is to maximize the current reward. Like, I don't think like we focus on maximizing the current reward because current reward might be misleading. So basically like the focus is to maximize the long-term reward. That too, like there are different variants. One is discounted and another is like total reward. So basically like it's like cumulative long-term reward. The agent performs actions in a deterministic fashion need not be, because like just previously we discussed that it can perform in an stochastic manner also if it maintains a policy which is stochastic. So this is also wrong. And we assume that the agent determines the reward. Again, like agent doesn't determine the reward. Like it is provided by the environment. So like this is also wrong. It is possible to have zero rewards. Yes, definitely. So in a game of chess, like all the intermediate, suppose for chess, all the intermediate rewards are given as zero, and maybe +1 for if you win, and -1 if you lose, and maybe for draw it remains zero. Or sometimes like they enforce a very, if you are very inclined towards winning, then you can give -1 for draw also, so that agent learns just to win. So this one is correct. It is possible to have zero rewards and reinforcement learning. If there is no doubt, I'll move to the third question. So this question says that we are taking actions according to Gaussian distributions, and the parameters are mu and sigma. This is the mu is the mean, sigma is the standard deviation. And we update the parameter according to reinforce. So reinforce is the algorithm which is used to generate the update equations, and AT denotes the action at time step t. So which is the like update. So basically we have been given two updates for mu. So basically like there are two parameters in Gaussian distribution, mu and sigma, and we need to like derive the updates for both of them. So let's see. So what is the like formula of Gaussian distribution? So like let's write this. We like we have mu and sigma, and this is given as 1 upon 2 pi, right, sigma, and e raised to power minus half. Then we can write a minus mu square upon sigma square, right? This is the formula of Gaussian distribution. So basically, according to this, we have to get the reinforced update. And what is reinforced update? For a general parameter, maybe suppose if the parameter was theta, then it will be theta t plus 1 is equals to theta t plus some alpha learning rate, that this reward. And here what it used to be, it used to be dou of ln of this pi. So I'm writing it just as pi, but you can infer that this is the pi I'm talking about, and this is with respect to theta. Why is this plus here? Because like we are performing gradient ascent. So in reinforcement learning, we perform gradient ascent and not gradient descent, unlike supervised learning. So now like basically like you have to like calculate this derivative for both mu and sigma and see like which one fits the equation. So maybe like I'll do it. So let's start with the mean first. So like this is the thing which we will be calculating for mean, right? Mu t, and it will be ln of pi of 80 mu t and sigma t. This is basically the formula, and this will become dou y dou mu t. And now you know like ln. So I'll tell you one thing. So you can see like we are calculating with respect to mu. So this whole entity, like it's kind of independent of mu, right? There is no component of mu here. So when we like kind of take ln, so you know this update, right? Ln of a dot b, like this is basically product. You can write it as ln a plus ln b. So we are using the same logic, but this thing is constant with respect to mu. So either way, like if we take the derivative of this entity, it will be gone to 0 because it is constant with respect to mu. But remember that it won't be constant with respect to sigma. So in first part, we can remove it. And there is this epsilon also. So you also know that ln of some epsilons a can be written as a, right? So we will use the same logic here. So here like we can write like this. So this will become minus 1 by 2 et minus mu t square upon sigma t square, right? Now you just have to take the derivative with respect to mu t. And like you know the derivative. So this sigma will be acting as a constant here. So basically you need to take the derivative of something like x squared. So it will be like minus half. And so this thing will become, so it will become 2 here. And once again, like when we apply the chain rule, one more minus will come. So this sign will be become positive and this will get cut. So it's like essentially 80 minus mu t upon sigma t square. So let's see like which option was correct. So this alpha and the RT will be definitely be there. So it's 80 minus mu t, not mu t minus 80, right? So first is definitely correct. And in a similar way, you have to calculate the uh, derivative, partial derivative with respect to this sigma. So let's do this also. So same thing here, just that uh, here like we cannot like eliminate that constant term, right? Because it is not constant with respect to sigma. This sigma is there, so we cannot eliminate it. So we have to keep it here. So it basically becomes uh, dou y dou sigma t, and this whole thing will becomes so ln of, so this we can take it to the numerator from denominator and insert a minus sign, right? So it will become minus ln root 2 pi, and this will be sigma t, right? Then like we will again have the same thing here. So this thing will remain same, right? So we will write it like minus half 80 minus mu t square upon sigma t square. And you have to take the derivative of this entity with respect to sigma t. So here again, like now you can apply this, this will go constant, so we can kind of remove it because derivative will make it 0. And basically like you have to take the derivative of minus ln sigma t, and this entity is like minus half. So all this like in this will be constant with respect to sigma, right? So we can like kind of, this 2 is already there. Okay, this was a square. And now basically like we have to perform this sigma 2 raised to minus 2. Like this I have taken to numerator. So you know the derivative. So this will become minus 1 upon sigma t, and this will become minus half. This will remain as it is, 80 minus mu p square, and this will become minus 2 will come again. So this will become plus minus 2, and this will become sigma t q. Again, it will be minus 3, so I'm taking it to the denominator. So this is cancelled. So it basically becomes 80 minus mu t square upon sigma t q minus 1 upon sigma t. This is the derivative. So we will check the answer. Like, is there same something here? 80 minus mu t square sigma t cube minus 1 by sigma t. So this is the answer, right? So 1 and 4 is the answer. So option 2 will be the correct answer for this. Like, is there any doubt in this? I hope not, because like this is simple plain calculus. Maybe I'll check chat once if there is anything. So nothing in chat. Maybe like I'll move to question number 4 now. So question 4 is assertion reason kind of question. So contextual bandits can be modeled as full reinforcement learning problem. Definitely, because like uh, sir also said in one of the lecture that contextual bandits are indeed one of the special case of full reinforcement learning problem. So we can model it. Even like not just contextual bandits, but we can like model just plain bandits as a stateless MDP. So that is also possible. And the reason they have given is we can define an MDP with n states, where n is the number of bandits. So suppose MDP with n states is there. The number of actions from each state corresponds to arm in the. So suppose if like there are n arms, then we can take uh, n is the number of bandits, we can take suppose k arms. So k actions with each action leading to termination of the episode. So in general, like full RL, what happens is this episode won't terminate after one step, right? Episode could be more than one step. So here, in case of contextual bandits, it will become one step and giving a reward according to the corresponding bandit and arm. So whatever like this pull of arms, suppose we pull K like one action, one or action and arm are analogous here. So 1 to K, like whatever we picked, and then we would have gotten some reward. So that will be the reward for this like transition. So yeah, like it can be modeled. Also, reason seems fine. So both are true, and reason is the correct explanation of aversion. Is there any doubt in this? So I hope not. Now I'll move to the last question of this segment, and it says, remember, like this is the discounted return formula. Gamma is a discounted factor, discount factor. Okay, so generally, like we have assumed that gamma should be like it can be equal to 0, but shouldn't be 1, because like if we are moving till infinity, then like this might become unbounded, right? So if we know like the horizon is finite, then we can use this equal to also. So which of the following best explains what happens when gamma is greater than 1? So they are asking what happens if gamma is greater than 1, suppose like it's 5. So let's see, like one option is nothing, gamma greater than 1 is common for many RL problems. Definitely not. It's not common. It's never used, in fact. So theoretically, nothing can go wrong. Like a lot can go wrong, right? If we don't use gamma, then suppose if the rewards are only positive, then this sum, like suppose if gamma is 5, right? Then like we will be multiplying it by 5 here, then 25 here, and simultaneously like it keeps on increasing and increasing. Then like it will be like kind of, it will almost tend to infinity. So like there are theoretical incorrectness here. So this is also wrong. The agent will learn that delayed rewards will always be beneficial, so will not learn properly, right? So this will happen because like agent, if suppose it was getting a reward of 1 here and a reward of 1 here, it will be amplified 5 times, and same reward will be amplified 25 times here. So it will be kind of learning in a wrong way, right? It will be thinking that we should like try to wait as much as possible. So this is the correct option. So this explains what happens when gamma is greater than 1. Again, none of the above is true. This is false. So this is the answer. So if there is any doubt in any of the 5 questions, now you can ask me. Okay, so maybe then I'll move to the next segment. So this is the like problem solving segment in which like I'll be taking up problems which are neither the part of programming like not programming practice assignment nor of general assignment. So let's see. Again, like this is related to calculation of reinforced updates. So in which the parameters on which the policy depends are the preferences of actions, and the action selection probabilities are determined by softmax relationship. Okay. So this is the like the thing which we need to keep in mind because this will be used in derivating. K is the total number of actions and theta I is the preference value. Okay. So derive the parameter update condition according to the reinforced procedure, considering the above described parameters and where the baseline is the reference reward. Okay. So we have seen this, right? We can subtract the baseline. Basically like this factor. So update goes like this. Theta I plus 1 is equals to theta I plus change in theta I, right? So they are asking us this quantity. So this quantity will definitely have alpha, and since they are considering this baseline, then it will be R minus B. This is the reward. So this is common factor in all 4. So basically like what we have to find out is simply the derivative, and the derivative is dou y dou theta. And with respect to theta, we have to find out this derivative, and it will be like ln of pi. I'm writing just pi, but you can understand that it is talking about this entire complex entity. So maybe like I'll do this. Right? So it becomes maybe like a like generally like sir have used t or you can use n, but here since they are using I, let's keep it I. So it becomes dou y dou theta I, right? And this whole entity. Now you need to again use that ln rule, right? So ln of a upon b, like you can write it like ln a minus ln b. And in a similar way, like we can write this. And also like there is a e there. So ln is already on base e. So ln e of a, we can write it as a. So again, like using that simplification, we can simply write this first thing will become like ln e raised to power theta I. So it will become theta I, just simply theta I. And first a minus will come because it was in denominator. And it will be ln of sigma j equals to 1 to k to k e raised to power theta j, right? Close this entity. Now, basically, we have to derive. So, like this will become 1. And now, again, like you need to apply chain rule. So first, like it will go in denominator, this sum j equals to 1 to k e raised to power theta j. Now this summation, right? So in this summation, like suppose if j is equals to I, then only like this is basically what is happening is e raised to power 1. Suppose 1 is there. E raised to power theta 1 is there. Then it will be e raised to power theta 2. Plus at some point it will become e raised to power theta I, right? And this will continue till e raised to power theta k. So all these apart from this term, like they will be like they will not depend on theta I, right? They are depending on some other theta, not on theta I. We are derivating with respect to theta I. So all these will be kind of constants with respect to this derivation. and only this term will be there. So this will go to zero when derivating, this will go to zero, all others will go to zero. Only this will remain. So, and the derivative of this with respect to theta, derivative of e raised to power something is equals to that same thing, right? So e raised to power theta I. Now this entity you can see, like this is simply the value of pi, right? Which was already given to us. So this becomes 1 minus pi, right? Pi of a theta something. And which is clearly this option, right? 1 minus. So this is the correct one. Is there any doubt in this one? If there is, then you can ask in chat or maybe unmute yourself and ask. Otherwise, like I'll move to next one. Okay. So now the question is, which among the following is are differences between contextual bandits and full RL problems? Okay. So the action and states in contextual bandits share features, but not in full RL problems. Like in full RL problems also they can share features, right? Some of the states, like suppose the state is like X coordinate, Y coordinate and time, then X and Y can be same for two state. So they can share feature, but time can be different. So they can share some of the features. So this is definitely wrong. This is not a difference. The actions in contextual bandits do not determine the next state, but typically do in full RL problems. This is correct because when we are considering, like we saw one question already regarding this, right? We were treating each of them as an independent problem, right? Like there were n states, so we were thinking that we should have n bandits denoting each of the state, and it kind of becomes independent of each other. So it's not like if some action you take here, like then it will determine that you will be going to this or not this. But nothing of that was happening. Everyone was kind of independent of each other. So this is the correct one. So actions in contextual bandits do not determine the next state, but typically do in full RL problem. Full RL problems can be modeled as MDP where contextual bandits problem cannot. Like we can obviously model contextual bandit problems also as MDP. So this is also wrong. And obviously like since this is correct, this has to be wrong. So this is the correct one. So is there any doubt in this? Okay. Then I'll move to this one. So given a stationary policy means that it doesn't change with time. Is it possible that if the agent is in same state at two different time steps, it can choose two different action? Suppose basically what they are saying, so you were in some state and then you like took action, moved around in the MDP, and then suppose initially it was at time step T1, then you came back to this state, T2. Then is it possible that you take two different actions at these two time steps? Like you are in the same state. So maybe like if they would have specified that our policy was deterministic, then this would have been true, right? Because deterministic means it's a mapping from state to action. So there could only be one action associated with one state. But since the policies can also be stochastic, so it can be different, right? So suppose if our policy is like, suppose actions are A1, A2, so probability 0.4, zero point 0.6 for A2. So first time we will generate a random number and see like accordingly if it falls, if we might get lucky, we might draws 0.39, then we will choose action even. Otherwise, like if it's like point five something, then we will choose action two. So it basically depends. So for stochastic policy, this is definitely possible that we can choose two different actions. And since they haven't mentioned anything about that type of policy, so it is definitely possible to choose two different actions at two different time steps, and we are in the same state. So yeah, this is possible. I hope like you understood this. If not, you can ask me. Okay, So if there is nothing, then I'll move. So in class, we saw that it is possible to learn via a sequence of stationary policies. During an episode, the policy does not change. So basically, like within an episode, we are following the same policy. So but we move to different stationary policy before the next episode begins. So this you can understand from like the perspective of chess. So you can think one episode as like one full game of chess, like it will result in either win, loss, or draw. Then like while you were playing this chess game, like suppose it's called this G1, then like you were following some policy and kept it constant while you are playing. Now, after it resulted in win or loss, then you will update your policy and then place maybe second game. Now, within this second game, you will keep again your policy as fixed stationary, and then like after the result, you can update. So this is what it means to say. Does the temporal difference method encountered when discussing the tic-tac-toe example follow this pattern of learning? So in tic-tac-toe, like basically TD updates are like those were happening at every time step, right? So while we are moving from T to T plus one, we were getting an update, TD update. And this is happening at the end of the episode. So if we are following this temporal difference method, then even within the episodes, we were making updates. So this is like different. Follow this pattern of learning? No, like it doesn't like wait for the episode to end to make the changes to the policy, right? It can make in within the episode also. So suppose in the game of chess, if we lost maybe the queen, like that is an important piece. So we might adjust the policy accordingly. So does the like follow this pattern of learning? So the answer is no. It follows a different pattern in which like at every time step will update, and this can happen within the episode also. And here like what they have given is like we are making the updates only at the end of the episode. So one thing to note here is that an episode can be of more than one time step, right? So suppose if we denote episode length, then this can be greater than one. Or like here we saw in contextual mandates like this problem. Here we can have like episodes which can end only in just one time step, but they're like in full RL we can have episodes which are much longer. So I hope like you understood the last one. Okay, then I'll move to the next one. So we saw the following definition of action value function for policy. So action value function is given as this: expectation under that policy of return, given that the state is S and action is A. Suppose that the action selected according to policy pi in state S is A1. Okay. For the same state, will the function be defined for actions other than A1? So suppose let's just consider A2, A3, A4 and all. Maybe AK action. And this is basically saying that will there be something like Q of S A1. So the policy says that it is like Q of like whenever S is there, suppose that the according to policy pi. So policy according to policy pi, like it is selecting action A1 in state S. So will it be like defined for actions other than A1? Definitely like you need to define for other also. Because like how will you compare otherwise that action A1 is better than action A2? Because if you are taking action A1 and the long-term reward associated with taking action A1 is more than action A2, then only like you can say that this is action A1 is better. And also like here, they haven't mentioned that the policy is like deterministic or stochastic. So it can be stochastic also. So obviously like it can happen. So we need to like define for not just A2, but for all A4. In fact, like basically like what we do is at every time step we will see the like q values of all the suppose we are in state some s, and we will see the q values of corresponding to all the actions and take an like argmax of this. So whichever action like gives you the maximum q value, then we will take that action. So it is like defined for all other actions also. So I hope like this is clear. Okay, then maybe I'll move to this one. So it's like 100 cross 100 grid world domain where the agent starts each episode in the bottom left corner. So there is a grid and the agent is starting somewhere here, right? And the goal is to reach the top right corner in the least number of steps. So in the least number of steps. To learn an optimal policy to solve this problem, you decide on a reward formulation in which the agent receives a reward of +1 on reaching the goal state. So first like is so it's like +1 if you reach this top right and 0 otherwise top right. Suppose you try two variants of this reward formulation. So okay, it's like in P1 you are using discounted rewards and in P2 no discounting is used. So which among the following would you expect to observe? So if there is like no discounting, then what will happen? Like, see, the goal is to like get to the top right corner, not just to get to the top right corner, but to get to the top right corner in least number of steps also. So if there is no discounting, so then like agent won't have any feel of urgency, right? So suppose this gamma is there and then you will be multiplying by gamma square gamma q. So if it reaches at a like later stage, then this one which he will be getting at the end, like this will get diluted. Maybe suppose if we reach at 1,000 step, this will be diluted very much. But if like discounting is there, then like this agent will feel that I need to get to that top right, not just to get to that top right, but I need to get to that top right in minimal number of steps. So discounting is actually helping, right? If there is no discounting, then what will happen? It like suppose if no discounting basically means gamma equal to 1, right? So it will be like you can reach in like 4 steps, then also total reward will be 1, and you can reach in maybe can be 1,000 steps and 1, then also like reward will be same. So agent won't be like prioritizing to go there in the least number of steps. So the options are like the same policy is learned in P1 and P2, definitely not. No learning in P1. P1 definitely the agent will learn. No learning in P2. Yeah, like this is there because it won't learn, because one of the learning goal is to reach there in least number of steps. If all the goals like not just to reach in the top right corner but also to reach in least number of steps, it won't learn this component. So if both aren't learned, then like we won't say that there is learning. So no learning in P2. Policy learned in P2 is better than the policy learned in P1. Definitely not. P1 is better. So I hope like you understood this question. If there is any doubt, like you can write in chat. Maybe I'll check chat once. Okay. Nothing in chat. Right. So this is like the last problem of this section before we move to the demo. So given an MDP, so we are given an MDP with finite state S and an arbitrary function F that maps S to real numbers. Okay. So F is basically mapping S to R. So what this basically means, suppose there are S1, Sn states are there. For each of the states, it will assign some real value. Maybe 2 here, 4 here, or maybe 1 here, something like that. So we are given an MDP and an arbitrary function. So these two are given to us. We don't have like control over these. The MDP has a policy pi such that f equals to v pi. So basically what this is saying is you can always find a value function pi. You can always find a policy pi whose value function is equivalent of this function, given function. But will this happen always? Like that is the question we need to answer. So suppose like if you consider a case where like in the MDP, like for any action you take, you are getting reward equal to 0. Like on every transition, the reward is 0. So for value function, like it will be like value function, you can calculate it in either way, discounted manner or total manner or average manner. It will be 0 in all the cases. And that will happen for all the states also, because for every transition, it will be 0. So if we have a value function like this, then if we are given an arbitrary function, then we won't be able to find a policy, because for every policy, it will be this 0 only, right? So in that case, this won't happen. So uh, it won't have always, right? So we cannot always have that. Okay, then like we are at the end of this problem solving section. If there are any doubts, you can ask in chat. I'll wait a few minutes before moving to demo, or you can unmute yourself and ask if there is any. Okay, since there is no doubt, I'll move to demo. So in demo, like what I have already shown is in week 1, we discussed exploration, exploitation, dilemma. This was in week 1. In week 2, we saw like if we are greedy with respect to just a mean, like UCB had two components. If we are greedy just respect to the first component, not the under root term, then what happens, and what if we follow UCB? And we got very good result with this UCB. And the problem remains same for today. And today, like we will be discussing two demo. Like first will be Thompson sampling, and second will also be Thompson sampling. But here it will be applied to the coin example. Here it will be applied to the advertisement example. So I'll like mention it again, like what this coin example is. So generally, like you have seen, like if you have a coin, like generally they assume that it's an unbiased coin, but our coins are biased. So this basically means that probability of head, it need not be like equal to probability of tail. It could be zero point 0.4 and zero point 0.6. And the goal of the game is to maximize number of heads. Because like if you get an head, then you will get +1 reward. If you get a tail, you get 0. So the goal is to maximize the number of heads. And again, like we will be considering 3 points and see like how we perform. So maybe like I'll start the collab notebook. I don't want you guys to see the probabilities. So I'll run it before sharing, then I'll share it. Okay, I hope like you are able to see the collab notebook, right? Someone can confirm me in the chat or just
Yes, we are able to see.
okay, okay. So you are able to see the collab notebook. Okay, then like I'll start this. So let's see how it goes. So we have like 3 coins. Number of tosses is 30, and these are the like so basically like we are following beta distribution. Maybe like I'll describe beta distribution first. So okay, I hope you are able to see the slides now, right? Okay, so you have heard of Gaussian distribution, right? In which the parameters are mu and sigma. So let me see if you can see this. Yeah, okay, you can see this. So here, like in beta distribution, we have parameters called alpha and beta. And the thing with this beta distribution is that it is defined on range 0 to 1. So unlike Gaussian distribution, which kind of like it can go till infinity from minus infinity to infinity, this is a like restricted distribution. And alpha and beta are the parameters of this distribution, and both alpha and beta are greater than 0. And the mean of this distribution is like this. It is alpha upon alpha plus beta, and variance is this quantity. So basically like this beta distribution, it has a PDF and CDF also. You can search on Wikipedia or in any probability book. So it's complex, like it involves gamma functions and all. So I won't be discussing that. But the idea behind beta distribution is that it has been used to model Thompson sampling. I'm not saying that you cannot use another distribution to model Thompson sampling. You can definitely use, but beta distribution is one of the popular one. And maybe you guys can take a guess. Like, does anyone have an idea like when did Thompson sampling came into existence? Anyone? Just take a wild guess in chat maybe. Just a while. Okay, 1700, 1990s. Okay, it's not that old also that it goes to 1700, but Thomson sampling was basically proposed in 1930s around by Thomson. You have heard Thomson, right? And the thing with this is that the belief, like basically like we represent the belief of true mean. Suppose an arm A is there. So basically what happens in this Thomson sampling is we assume that there is some distribution. Suppose this is arm A1, this is arm A2. Some distribution is there over these reward arm, maybe AK. And the aim is like by observing samples, like we try to fit these distributions. And with more and more samples, we will get closer to the true distribution. And then at every time step, what we do is we will sample from this distribution, and whoever gives the maximum, like we will pull that arm. So this way, like Thompson sampling works. And the belief about the true mean of an army is represented using beta. And now here alpha we take as SAT plus 1. What does this mean? S denotes success, and A denotes that arm A, and T denotes time step. So basically in our coin problem, this becomes number of heads, right? Number of heads is success and number of tails is failure. So how many tails you have accumulated for a certain coin? So there are 3 coins in our problem. For every coin, we will be counting like suppose we have tossed 10 times and how many heads. So heads will be success and tails will be failures. So till that time step, how many heads and how many tails. That is represented by this success and failure variables. And we assume that we assume some kind of belief that over this two distribution, like it is represented by this distribution beta of those number of successes plus 1 and failure plus 1. So this is a quite a standard way of doing Thompson sampling. And now I'll like show you the collab notebook. Okay, so according to those distributions, it has given us, I hope you can see this screen. So it has given us 3 beta values for all 3 coins. It's 0.37, 0.37 for coin 1 and 2. And yeah, So it's 0.91 for coin 3. So basically we are sampling at every time step, and whoever, whichever coins gives the highest value, we will like pull that coin. Here I'll say pull coin or toss coin, like it's equivalent. We are using coin. So generally in literature they say pull the arm, toss the coin. So equivalent, they are equivalent to each other. Okay. So we will toss the coin 3 and let's see. Coin 3 gave us an head, but there is some randomness, right? So this is how like this Thompson sampling is, that exploration exploitation dilemma. So this is how it's enforcing. Even though like we got head on coin 3, it's not saying that no, you go and pull coin 3 again. So it is like kind of generating and kind of trying to explore initially. So we do to coin 2. Now, after coin 2 is full, it gave tail. So this is slightly hampering the coin 2. Now it goes back again to coin 3 and it gives 0.82. So we will pull coin 2. Now, see, even though we have got two heads, but still it's saying like go back to coin 1 because you haven't explored it. So we go to coin 1. Now, once we go to coin 1, it gave tail. So all these three coins have certain probability of heads, which I will reveal at the end. So that you don't have like, you don't know which is the best coin. So maybe coin 1 or coin 2 are the good coins, but they might got unlucky on the first one. So now it's saying that pull coin 2. Okay, so we toss coin 2. Coin 2 gave head. But now it has kind of realized. So now it's like in the stage where it has started like fitting those distributions. So it is like drawing from those distributions, and this time like it drew the highest beta value from coin 3. So let's see coin 3. Now we go back to coin 1. Even though like you see like there are three heads, three consecutive heads, still it wants to give chance to coin 1. So we go to coin 1 again. Now we go to coin 3. Coin 1, like it gave two tails. So it is kind of, maybe it might be a bad coin, but we will explore and like we need to draw more samples, right? So we do that. Let's go with coin 3. Now, even though like it's four heads again, but still it wants us to explore coin 2 some more. Let's go with coin 2 then. Now we go with coin 3. And in a similar way, like we have already completed 10 tosses. So we'll do 20 more and see like what happens. So now it says that go to coin 2, we go to coin 2. Now it's like coin 2, you can see like it's almost 50 heads and 50 tails. And coin 3 has given us 5 consecutive heads. So maybe coin 3 is the better coin, but let's do the experiments. Coin 3 again. Then coin 3. Now you can see like it has kind of found out that coin 3 is indeed the better coin. Now it's kind of giving value closer to coin 3. So coin 3 actually has a distribution which is like quite high towards reward 1. So I'll tell you like what the exact distributions are, but as of now, we will keep on pulling coin 3. So again 3. Now again 3. Again 3. So again 3. So now it has kind of, so basically what has happened like coin 2, like it kind of gave two consecutive tails. So it wants to like explore coin 2 maybe one more time. Let's see. Coin 2 gave an head, but still like it's like three heads and two tails, but this has a lot of heads and a few tails. So go to coin 3. Now coin 3 gave head. So we are favoring coin 3 again and again now. Coin 3, again coin 3, again coin 3. So four more tosses are left. So at this point, you can see like it's kind of sampling coin 3 again and again. It is kind of indicating to us that go for coin 3. Again coin 3, again coin 3. I think like we have completed the 30 tosses. So it is like total heads which we got is 23 out of 30, which is not bad, right? Now I'll show you the actual probabilities of these arms. So coin 1 was indeed a bad coin with 0.2 probability of head, and coin 1 was with 0.2, coin 2 with 0.5. So it's like kind of unbiased coin, and coin 3 had a higher probability of heads, 0.8. So suppose if we didn't explore coin 1 and coin 2, simply exploited coin 3 from the beginning, then in expectation we would have got 24 heads, right? But what we got is 23. So one is our regret here. So in this way, like this Thompson sampling works, right? I hope like there is no doubt in this. We will check chat once. Uh, Someone is saying bias. Uh, which bias can you like tell me, confirm me? So basically like the bias, you're asking about uh how these coins are biased, right? Yeah. So here it is mentioned in the beginning itself. I'll show you. So this P is a list which contains probability of head of all the 3 coins. So for coin 1, it's like 0.2 probability of head. So it's biased because it is biased towards tails. With 0.8, it will pick tail, and with 0.2, it will pick head. Coin 2 is unbiased, 0.5 to head and 0.5 to tail. Coin 3 is again biased, 0.8 to head and 0.2 to tail. I hope like that clears the doubt. Yeah. Okay. So I hope like this example kind of clarifies to you. So in a similar way, like we did it for UCB also, right? So maybe like let's try UCB once more and see like whether UCB gives the better one or this Thompson sampling. Let's run UCB. Okay, so UCB values like like initially it's not defined due to because we haven't pulled any of the arms at the beginning. So in UCV, like we need to pull all the arms at least once and then we proceed further because otherwise that quantity, second term, it contains in denominator, there is a component of number of times that arm has been pulled. So that is 0. So it becomes undefined, right? So maybe like for the first 3 tosses, we will simply do all coins once. So 1 and it gave tail. So its UCV value is 1. Its UCV value is 0. Now we do coin 2 once. Now coin 3 once. So now you have UCV values of all 3. Now from now on, like we will be pulling the arm or tossing the coin, whichever has the highest UCV value. Okay. So as of now, it's coin 2 and coin 3, right? So maybe like we do tiebreaker and give coin 2 the advantage. And now you can see UCV value. So how this is happening is even though like the mean value returned by this coin 2 is 1, but since coin 3 hasn't been explored much, so UCB is kind of telling us that go and explore coin 3 because like coin 3 has in denominator 1 and this coin 2 will have 2 now, right? So due to that second term, this difference is coming. Although like first term is 1 for both of these. Now we go and explore coin 3. Now you can see like both will have same UCV values because like both gave heads and both have been tossed 2 times. So maybe like again like last time we gave advantage to 2, this time we give advantage to 3. So now we can see that the UCV value of coin 2 became more. Although like head number of heads is more for coin 3. Now we go for coin 2. So now you can see slightly also that this UCB value of coin one keeps on increasing. It was 1.89, even though we are not pulling it, it became 1.97 because this UCB has an inherent capability to tell that you need to explore also. So this keeps on increasing. There will come a point if we don't pull coin one, then it will automatically surpass these UCB values of other coins. So as of now, we pull coin three. Okay, so now you can see that point has come. Even though like for coin three we have four heads, but due to that second term, like it tells us that no, go and explore coin one further. So we go and pull coin one. We did it correctly, right? Yeah. So now coin one gave two tails. So it might be a bad coin, right? So now it's recommending us to pull coin three. Now again coin three. Now it tells us to pull coin two. Now coin three. So in a similar way, like we will continue. Now coin three. Now coin three again. See again coin one we haven't pulled, but its UCB value is increasing. But if we keep on getting heads for coin 2 and coin 3, then their UCB value will also increase. So let's pull coin 3. Now you see there. Again, coin 3 is still better. Now we have to pull coin 2. So how many tosses are left? 13 more. So now see, there comes a point where like UCB value of coin 1 has increased again. Now we try it once more. Again, it gave tail. So it is definitely a bad coin. By that time, UCB would have realized it. Now it probably won't recommend coin one. Let's see if it does. So as of now, we pull coin three. Now again coin three. Again coin three. So 5 3 coin three. Again coin three. See now we go back to coin two. Coin two gave tails. So you can see like coin two, two heads, four tails. It is also showing that it is also not that good. Although like coin one is quite bad. But as you can see now, it wants us to explore coin one once more. So let's explore. Four tails, consecutive tails. Now it's recommending us coin three. Now we go to coin three again. Coin three still. Coin three. Coin three. Okay, finished. Right now we are done. Let's see. So we got 19 heads. So you see, like this is the difference. Like with Thompson sampling, we got like how many heads? 23 something. And regret was just one. But with UCV, we got 19. So regret is 5 because in expectation, if we were pulling coin 3, then we should have gotten to 24. So this Thompson sampling is actually like more, it matches the bound. Like there is a bound given by Lai and Robbins, and this Thompson sampling actually matches the bound to the level of constants. UCV matches in just order, but not the constants. So those constants make a lot of difference, especially when we are like doing a small number of tosses. 30 is relatively small, right? So now like I'll move to second demo. So I hope like there is no doubt in this demo. If there is, maybe you can unmute and ask, or I'll check chat once. Okay, so there is no doubt in this one. Right. So I'll move to second demo. So you can okay. You can see like the second one I have it on Kaggle, right? So first one was on Google Colab. So these are like basically the two platforms which you can use for making notebooks. So the difference basically is like in Google Colab, suppose if you put some data here, upload some data here, and when this session gets disconnected, then what happens is we will like kind of lose that data, and we'll have to like again upload this data here. Or one option is to like put it in your Google Drive, but generally what happens when the data is quite large, Google Drive, like the space is limited, like 15 GB is free. So sometimes like data sets are bigger than 15 GB. See here also they have given 81 GB space. So these are the like advantages and disadvantages of Google Colab. So Google Colab, like the uh, UI is quite good, like in looks and all, and also like uh, this autosave feature of Google Colab is quite good. Otherwise, like sometimes what happens in Kaggle, if you don't save, then this data, like whatever code you wrote from the last save point, like it gets lost. So this I have faced many times. So I had to rewrite the code again. But the good thing with this Kaggle thing is like once I upload the data, suppose this is the CSV file which I wanted to upload, even though like I can close this session and come back, this CSV file will still be here. So it won't get deleted, unlike Google Colab. So you can like use both platforms according to your need. Also, like Kaggle provides you free GPU support. So these are the like GPU, and it's like free GPU like 30 hours per week. That is quite a lot. So Google Colab, like you might get first maybe some minutes, and otherwise you'll have to purchase. So Kaggle provides you free GPU support for 30 hours per week. So if you want to use that, then you can use Kaggle. So these are basically the differences between two platforms, Google and Kaggle, Google Colab and Kaggle. So now like I'll show you another demo. Like in this also, like it will be Thompson sampling to import pandas. Like pandas and random and matplotlib, these are like quite common. So we are reading the data. So here you can see like I have this data. So in the same folder, I will be sharing this CSV also. But here like I have it here. So I have like copied this part and pasted that part. But if you want to do it in Collab, then you will have to specify if you are reading from your Google Drive, then you'll have to specify that path. Otherwise, if you are using Kaggle, you can simply upload it. But this like names and all like these can change. So you'll have to accordingly copy the path, appropriate path. So what is happening? So in the previous example, like there were three coins for us. Here now we are considering 10 ads. So you can consider these advertisements as the number of arms. So basically like there is, and we need to show, suppose on your mobile phone, there is a space of ad. We need to show one of the ad, and all of these ads have like probability of getting clicked. Maybe ad one is highly probable to get clicked because it is like quite good, or like it attracts a lot of customers. Ad 10, maybe it's like quite boring ad, so no one pays attention, no one clicks to it. So all those kind of thing is there. So there like we kind of assume that coins were biased, right? We had those probabilities, but here like those we don't have those probabilities, but what we have is this CSV, and this is like the data. So from this like we can kind of get an estimate like which ad is good. So I won't be revealing like beforehand that which of these ads is good. We will be seeing from the data, and there are like 10,000 data points. So for 10,000 time steps we can train. Now let's see in the previous one we did it for n equals to 30. We did 30 polls, right? So now we will start with 30 and let's see like what happens. So you might think that like for three coins, 30 seems not a bad number. But for 10, it will be like maybe if we are giving three to each on average, it might be less. So let's see how is the performance with 30. And so maybe I'll explain this code first. And D is basically the number of dimensionality of arms. So it's 10 here. Add selected. So this is the list in which like we will be appending at every time step which ad got selected. And again like successes in our case, like their case it was head. Here success will be whether the user clicked the ad or not. So we are initially we are denoting the successes of all 10 ads as 0, but eventually like if some ad get clicked, then we will be adding 1 to that number for that point, for that like advertisements. And similarly failures, if like ad get showed up and it didn't get clicked, then it's a failure. And total reward, like is whatever, like this is like not ad specific, like this is basically like how many clicks we got. So basically you can think this total reward from the perspective of the platform. Maybe Google is there, or maybe YouTube is showing some ads. It will be showing all the 10 ads, and whatever like expect like profit it got is that like total profit. It need not be like from ad specific. It will be total profits all of all the 10 ads. So what is our aim? Our aim is to like kind of find out like we need to show that ad again and again, which has high probability of getting clicked, right? So we need to find this through bandits. So this is the like loop. We are like doing it for n. So initially we have n30, and this is basically the ad index 0 max beta. So in this loop we are doing nothing. We are basically like sampling from this beta distribution. So I mentioned this, like we will be sampling from our beta distribution, which is successes plus one and failures plus one, and this we are doing for all the d coins, which is 10 coins, 10 ads, sorry. And we are basically finding whichever ad gave the maximum beta value, then we will be like putting that. And here like we are getting the reward from the CSV file, because we don't have probability distribution or even the probability. Otherwise we could have simply generated from random number, but here like we are getting from this. So maybe like it's like if time step 0 at 1 was shown, and it would have got clicked, so it got 1 in a similar way. So these are like independent of each other. So there might be a like time where like none of the ads got clicked. Okay, so this is the like formulation. And again, like these are the updates here. So if reward is 1, then we are updating the successes. Initially we had 0, like for all the 10 ads. And otherwise, like we are updating the failure, and we are adding the total reward also. And this is simply for plotting purpose. So I'll like maybe run for 30. Let's see what happened. So in 30, like you cannot kind of differentiate that which ad is good, right? So maybe for coins, we were able to get decent amount of uh, like less regret and decent amount of profit in terms of number of heads. But here we need to do more. So maybe like I'll do for 100. So we already have 10,000 data points, right? We can go till 10,000. So I'll go for 100. Let's see what happens at 100. 100 also, like we cannot kind of distinguish like which ad is quite good. Like here it's saying that ad 8 is good. Let's go till maybe 1,000. Let's see what happens with 1,000. Now we can see some difference. Like this is significantly higher than others. So we can kind of see that at 5, maybe it has a higher probability of getting clicked. So we can see out of 1,000, almost 380 something ad 5 is getting shown. Now I'll do for maybe 5,000. Now we are quite certain that ad 5 is the best ad, and maybe ad 8 is not that good. Like it's good, but like compared to others it's good, but compared to this ad 5 it's not that good. So maybe we can say that ad 8 is the second best ad. So let's do use the full data and see like what is the final performance. So this is like Thompson sampling happening in the background. Right now we are quite certain. So we can you can see like ad 5 is definitely the best ad, and it's like around maybe 9,500, I guess. So out of 10,000, 9,500 times at 3 is getting shown. Like we are pulling that ad, and ad 8 is the second, maybe around, I don't know, 400 or something. So let's see, like I have already this. So let's see like which was actually the best ad. So here you can see ad 5, like it has the highest ever 2695. And after that it's 2091 of ad 8. So if we do a long number of times, like large number of times, around 10,000, like the beta distributions, they are going to fit the true distributions almost perfectly. And this is seen in this example, right? And now I'll show you total reward also. So total reward is 2601, right? So this is what we accumulated. But if we pulled only at 5 from the beginning itself, we didn't give chance to the other ads, then we might have gotten 2695 in expectation. So like this 2695 minus 2601, which is 94, is our regret. So I hope like you understood this question. I'll check chat once. There is something. Okay. So and I hope that you guys like understood the code for this one. Like I shared it last week, right? So I have been sharing these. So I'll maybe tell you like how this is happening. So these are like simply importing of the libraries. Then seed, like seed basically means that you can reproduce your results. Number of coins 3. These are the probabilities of heads. Total number of tosses you can decide here. So this is exploration and exploitation. In this, like nothing much was happening. In which, like basically, we were determining the coin to toss according to the results. We were doing it manually. So all this code is simply to like print these outputs and like some random numbers. But I'll show you the main logic. And here, like we were in second one, we were being greedy with respect to mean record. So this is basically the first term of the UCB term. Like there is two terms in UCB. Like first is Q value estimate and plus under root of 2 ln total number of poles upon number of poles of that term. So this, if we are greedy with respect to only the first term, then like we were kind of like suppose there is a this means of these coin. Initially we append a 0 to like all three coins have mean 0, and then as and when like we were getting those coins, we were like uh, updating the means. So this will become how many times we got heads and total number of tosses of that coin. And in a similar manner, like we were calculating UCB also. So UCB also requires mean because means is the one of the term of UCB, right? So initially, like for UCB, we appended not defined, for means again 0. And in a similar manner, like we are like here we are doing that UCB calculation. And I have inserted this if, so that like if, because in UCB, like we need to ensure that every coin is tossed at least once. So until that coin is tossed, we won't be assigning values to UCB. So once that is done, like number of tosses of each coin becomes not equal to 1, basically more than 1, then we will be assigning UCB. So this will be basically like means plus this square root of log of total tosses upon tosses of that coin. So this is how we are calculating UCB value, and all this remaining code is simply to print this stuff. So this is like the UCB one. This is the main part where calculation is happening. Then I'll show you similarly for Thompson sampling. So Thompson sampling, we don't need means, right? We need only successes and failures and beta values. So here, like if we are getting like heads, then we are increasing the like basically like here like what we were doing is we are either way like doing this outcome. So we are counting how many number of heads till that time and how many number of tails. So we are not doing it in an iterative manner. We are already doing this outcome insertion because it was needed for printing this thing. So we are simply counting from that instead of doing it repeatedly. And now like here like beta values, like we are again generating from the beta distribution, and these are the parameters: successes of coin plus 1, failures of coin plus 1. So these are the parameters. So in this way, like we were generating those beta values. So I will be sharing these two files with you. Also, like for this second demo, I'll be sharing this CSV file also. So maybe you can play around. I have done this one for 30 tosses. You can do for more. And there are many problems and bandits you can try. And also like I have done for UCB Thompson sampling, but there are other algorithms which I missed, like the median elimination, right? And there was a naive algorithm also, so you can do that. And there was one more I mentioned, KLUCB, so you can try, like there are different variants of UCB, so you can try those also if you have time, obviously. So now I'll like move to slides again. Yeah. So, right. So I hope like you are able to see the screen now, like the slides. So, okay, so slides are visible. So I'll move to our last segment for today, which is the assignment 3. So as usual, like since the deadline is still there, Wednesday, I think 11:59 p.m. Then I won't be giving you answers, exact answers, but I'll be guiding you towards the answers so that if you have watched the lectures, you can solve it yourself. So, which of the following is true for an MDP? So, basically, like this is asking something, and this is saying that probability of ST plus 1 RT plus 1 is independent of last like state and action. Does this like basically like all these probabilities, there is a property called Markov property. So it is kind of asking like which one of these actually specify the Markov property. And in Markov property basically says that only current state is enough. No dependency on history. Right. So this first option is saying it doesn't depend on the current state and current action or also. So this is definitely wrong, right? And this one is saying that it depends always on the initial state and initial action. So this is also wrong. And this is quite bad, right? Because like it's t plus 1 and rt plus 1 here, and it moves to previous steps probability. So this doesn't happen. So I think like like this is the history, right? So instead of depending on the entire history, history will mean like this is the history for the current state t, and this is the current state. So it basically depends on current state only, not on the history associated. How we got there doesn't matter. So this is like what happens in game of chess, right? Suppose in a game of chess, maybe chess is complex. I'll take tic-tac-toe example. So suppose this is the state. You might have reached, maybe some agent has uh, first took this, then like second move like this happened, then this happened, right? Or it could have happened like first move was this, then second move was again this, and third move was this. So both ways, like you have reached the state. It doesn't matter how you reach that. If once you have reached that state, like that state is sufficient to supply you the next move. So there is no component of history in such problems. So in such problems, you can use Markov property. So I hope like this is clear to everyone. Okay, so if it's clear, maybe I'll check chat once. Okay, so now I'll move to the second question. So the baseline in the reinforce update should not depend on which of the following. Okay, without voiding any of the steps in the proof of reinforce. Okay, so baseline should not depend on what? So I'll give you a hint. Like one of the baseline, popular baseline is average of rewards. So average of rewards will definitely depend on the reward at previous time step. Like this average will obviously be calculated using this, also this. So these two, like obviously there is a dependency, right? So these two cannot be there. So it should not depend on which of the following, right? Rn1 it is depending, Rn it is depending. Can it depend on action? Like, right, like it is a baseline, right? Baseline means something which is common for all action. baseline subtraction happens there. You might have seen in one of the previous formula, this alpha was there and some derivative, like theta of ln of pi. So it is like this should not depend on action. Now I hope like you got that idea. Is there like any doubt in this one? Okay, then I'll move to the next question. Okay, so another important point which I wanted to mention. Do you know like what these squares mean? Like generally, like in previous question, it was circles. Here it's a square. Can anyone write in chat? Multiple choice options, yeah. So yeah, that's right. So this you need to be careful of because no one is going to tell you this. So if you are given circles, this generally means that it is a single option correct. Only one of the four options will be correct. And this means that it is multiple option correct. It's not saying that it's not possible that only one of them is correct, but it could be possible that more than one can be correct also. So this you have to infer it yourself. Either way, like when you are on the platform, you can check it by if you are clicking this option and then you click this one. If this automatically gets unclicked, then it's single option correct. So this circle and like square is quite the common one, but you can check it manually also. So that is the thing. So this is a multiple option correct. So more than one can be correct in this one. Right. So, okay, then the point is in many supervised machine learning algorithm like neural networks, we rely on gradient descent. Okay, so I have mentioned this once before also. So gradient descent is kind of so what basically happens in gradient descent. Suppose this is our error function, right? This is like y-axis is error, and this may be you can say some space in which we are searching. Right, so we need maybe I'll write it W. W denotes the weight of the neural network. So we need to find the optimal weights of this neural network, and we can see like this is the global minima, right? So we need to reach this. But generally, what happens is we cannot so most of these error functions they cannot be solved in closed form. Some of them have closed form solution, others might not have. So like generally we follow an iterative kind of thing where we like kind of move. So if we have to do descent, then we move in opposite direction of gradient. And but sometimes what happens is we might get stuck here. So concepts of momentum and all come here. So this is like how gradient descent works. So what they are asking is like they are simply mentioning that in supervised machine learning algorithms like neural networks, we use gradient descent. However, in policy gradient approach to bandit problems, we make use of gradient descent. So I'll mention this also. So generally like the update in gradient descent is theta t minus something alpha or upon theta t, and this is some error function, right? So we are moving in opposite direction. This alpha is positive, definitely learning it, and we are moving opposite in direction of this gradient. And in gradient descent, this minus becomes plus. So we are moving in direction of gradient. So here you can see. So in like RL, our objective is to maximize, right? So our goal is suppose this is the optimal value. So we move in direction of gradient. And how this happens is I'll tell you. Suppose you know this, right? This is the maybe the curve of x squared. So its gradient is 2x. So it is like as we are moving, the gradient is increasing, right? So we move in opposite direction of the gradient. And this is a convex function, then there are concave functions. These are like well-behaved functions. But generally, like what happens is these, suppose in case of supervised learning, there is error. And in case of here, it's reward. Like reward also, you can write value function also. So like return maybe like basically the idea is to maximize. So here the idea is to minimize because error is something we want to minimize and reward is something positive which we want to maximize. So the discrepancy can mainly be attributed to differences in. So basically, they are asking why we are performing gradient descent in neural networks and gradient ascent here. So like the objectives of the learning task, definitely like objective one is like in neural network is minimization, and in and this policy gradient is maximization. So objective definitely due to that there is a difference, right? The parameters of the function whose gradients are being calculated. Mm, will this make a difference? Like suppose x squared is there or something like parameters of the function won't influence this, right? That we are performing gradient descent or gradient ascent. So this won't be influencing much. The nature of the feedback received by the algorithm, right? So error in neural network, we get error kind of feedback, and in policy gradient, we get reward kind of. So feedback definitely determines, because error is something which we want to minimize and reward is something which we want to maximize. So nature of feedback definitely. But you need to find out whether it will depend on parameters of the function whose gradient is being calculated. So like gradient is an entity here itself, right? For the second one, I didn't write the equation. Delta here maybe some g, I like g upon delta theta t, right? So this gradient, like it's common here, like but the sign, even without this gradient, like there is negative sign here and there is positive sign here. So it really shouldn't depend on parameters of the function, right? Okay, then I hope like there is no doubt in this. I'll check chat once. Okay, so now I'll move to the next question, which is fourth. Again, like something related to solving. In case of linear bandits, we did something similar there also, but here the function is slightly different. It's two action. There it was like k action something. Also like this. There it was just theta. This weight vector is there. So this denotes dot product. So this is like a vector. So now like here state is like multiple dimensional state. So I'll tell you how this state. So I mentioned once that is one state could be x coordinate, y coordinate, time, and like what is the like kind of weight, right? So you need to see this. So it's usually like this you take transpose and by default it's column vector. So this becomes the dot product. And again, like we are doing something kind of softmax. So the policy pi to be followed when encountering a state as is given by. So this is the policy. For action A1, it's this. And for action, I think this should be 2. Wait, this is a mistake. Wait, I'll check once. Yeah, it should be 2. So this is the policy which we have been doing. So this basically knows the probability of taking action. Suppose we are in state S, and what is the probability with which we take action A1, and what is the probability with which we take action A2. And now, like these are the weight vectors, okay, associated with action. I mean, if we are using reinforce to update to learn the parameters, what will be again like same kind of reinforce update? What will be the update for W1 and W2 when we pull action A1? This is the important thing. So we are talking about only the first part, not the like second part. Okay. So again, like the same equation. So we need to find it for W1 and W2 and see like which one is correct combination. So again, like this component is common. Alpha, 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 alpha is the learning rate, R is the reward. So basically, like we just have to find this ln of pi. Pi by default refers to this one, and whatever W1 or W2. So let's do this. Okay, so first let's find for W1. ln of phi a1 of x, right? So one thing you need to notice, like this is asking for like only the action a1. So in both cases, you will be differentiating with respect to first term only, not the second one. If it was asking with respect to a2, then you will be using this second term. So this will become do y do w1 again, like you have ln there, so ln of e of this thing, this will become w1 transpose s plus, then we will have ln of this summation, ln of e raised to power w1 transpose s plus e raised to power w2 transpose s. Okay. Now we are like derivating with respect to W1. So this derivative, you might have done vector kind of derivation. So this will be S. Now for ln, like again, like this whole thing will go to uh, denominator. Now using chain rule, we derivative with respect to W1. So when we are doing with respect to W1, this term will be kind of constant for W1. So this will go to 0. Now we will be derivating with just this term. And again, like we will be applying chain rule. So for here, like it will be but this only, but we need to derivate again this also. So when we derivate with again this W1 transpose S using chain rule, then it will become S. So this is basically what we got. S plus this sum into S. So where is this? Oh, wait a minute. There is there some mistake which we made? Okay, yeah. Here, like it will be ln minus, right? Because like ln, it was a upon b. So ln a minus ln b. So this will be minus. So here it's like S minus this thing into S. Okay, so first one. So in a similar manner, like you need to find out what happens in this W2. So, but the thing to remember is you need to derive this entity because it's asking with respect to action even. So when you do that, you'll find out what is the update for W2 and you can simultaneously find out the combination. Definitely, like since it's one, these two are ruled out. Now you need to find out whether it's 3 or 4, right? So is there any doubt in this one? Okay, so there is no doubt. So I'll move to fifth one. So what does fifth one say? The update in reinforce is given by this, yeah, new one plus alpha ln, okay, where is an unbiased estimator of the two gradient. Okay, so basically like this means is that we are using, so in neural network there is a concept called stochastic gradient descent. Here we use stochastic gradient ascent. So generally like there are properties of this stochastic gradient descent. Actually, like what happens with this is like uh, there are three versions of this gradient descent. One is like full gradient descent, and analogously it will be for gradient ascent also full, right? And there is one called mini batch for both GA and GD, and the extreme version is stochastic. So in full, what happens is we are like kind of our, in case of GD, our error function will be like summation over all the data points. In mini batch, it will be over a subset of data points, and in stochastic, it will be just one data point. And in a similar manner, this happens analogously for gradient descent also. If we are considering all the data points, then it will be for like full gradient descent. If we consider only a subset, then it will be mini batch. If we consider one, then it will be stochastic gradient descent. And here, like we are doing with respect to just one, right? So there is no sigma. So that's why like this is stochastic. Who is an unbiased estimator of the two gradient of the performance function. However, there was another variant of reinforce. Okay, we saw this with a baseline that is independent of the action taken. Yeah, like this we know that the baseline should be independent of the action taken and is subtracted from the obtained reward. Yeah, this is the update there. So we are basically asked that baselines, like if we are subtracting some baseline, and if we are not doing that, like what is the relation between these two things? So will it be equal? Will it be like one is lesser than or other is greater than? So maybe like I'll solve some part. So let's begin with LHS. So this expectation, we can write it like, so expectation we can write like this first one RT and this dou I dou theta T. I won't write full, I'll write just by, right? Minus expectation of with respect to B and again this term. So, and the relation is with respect to expectation of RT d pi upon dou theta T RT. So basically like this is the term of focus. So we need to find out whether this could be equal to 0, is this lesser than 0, or is this greater than 0. So we need to find that relation, right? So we'll start with this one. So let's see. So this expectation is over action, right? So I missed Ellen here. So let's focus on this term. So maybe minus we will see later. First focus on this one. So B, now when we derive with respect to ln, so it will be like 1 by pi, right? Something, the same entity, and then it will be dou pi by dou theta t. Okay. Now this is expectation. So expectation, do you know like what is the formula of expectation? Expectation can be written as summation of some probability, right? Into whatever value we are calculating over expectation. So expectation is some kind of averaging. So probability of maybe something and like what is the value associated with that probability. So we can write this expectation as sigma over actions. So this expectation is over pi, right? So this is basically means that actions. And now we will be doing this dt pi by theta p. And this will be getting multiplied by some probability, and this probability is basically our pi. So that I'm not writing completely, but you can understand. So this will, these pi's will get cancelled, and we have sigma over a. Now what we get is b. Now b upon dou pi by dou theta t, whatever. So we also know that this b is independent of a, right? So it can come out. So it will be b sigma over a of this gradient. And you need to, like, till now I was writing just pi. Now you need to write it fully. So it is pi of at theta t. So this is over all the actions. Now what you need to do is you need to find out what is the value of this. So do you know like there is a rule in derivative. Derivative of suppose x, some function f plus g plus h. This can be written as derivative of f upon derivative of x plus derivative of g upon derivative of h. So similarly, like this summation, like we have right hand side here, and this is h also. Maybe I'll remove h from here. So this summation we have here. So we can write it in this form, right? So this sigma can go inside. So it will become finally v into sigma is going inside dou upon dou theta t summation of these pi's. But you know that this pi, summation of pi is basically this pi represents probabilities of each action, right? So this summation over action, this will sum to 1 and it will be a constant, and derivative of anything with respect to a constant is 0. So this entity will be 0. So accordingly, like this will be 0. And I hope like you got the answer. So is there like any doubt in this one? I hope no. Okay, so 5 questions have been done. Now I'll move to the sixth one. Okay, we had an extra page. Either way, leave it. So the sixth question says, consider the following policy search algorithm for a multi-armed bandit. Uh, okay, so okay, so they have basically used indicator functions here. But when you like do this, suppose if for RT equal to 0 and RT equal to 1, you'll get two individual equations, right? So which of the following is true for the above algorithm? Is it LRI algorithm? What happens in LRI algorithm? Do you know? So basically like uh, how Sir taught is like there was for one it was alpha and for second it was beta, right? But here we only have alpha. And for LRI, what was happening is like beta equal to 0. Uh, okay. And for this, alpha was like very, very larger than beta. And now there was one more, RP, for which alpha equals to beta. So this is definitely like this one because like when you reduce these equations, you'll see like there is no beta appearing. So basically alpha equals to beta. This equation will reduce when you apply the indicator functions and all. Now what happens is, so basically like you have to make two test cases, like two cases and like uh, open up these equations and see like it reduces to something. And then you need to see like whether beta is appearing. It won't appear, obviously, it's not there. So the question now reduces to, it's RP, you can take it from me, but what is the property of RP? This was covered in lecture, like whether it works in the case where suppose there are two arms, west arm has zero point 0.9 and second west has zero point 0.5, or it works better when like those are close. So when they are close, I think like LRI works better, right? But when they are not close, then we can use LRP. So you can think it that way and see like which is the answer. Now I'll move to seventh one. So seventh one says that the actions in contextual bandits do not determine the next state, but typically do in full art. Okay, so like I think like we have seen this statement in one of the previous problems. So you know the answer. Like I won't focus much time on this question. So in a continuous state environment, continuous action space environment, we can employ any value-based function, value function based algorithm to discover an optimal policy. So generally, like one of the advantages of policy-based methods, one of the, in fact, the biggest advantages of policy-based methods is it works in continuous spaces. This is one of the biggest advantages of policy-based methods. And the reason people came up with these policy-based approaches is because like they were having difficulty applying value-based methods in continuous action spaces. So I'll tell you like how value-based action, like value-based approaches work. Suppose maybe use a, you guys, has any one of you like heard of term deep reinforcement learning? Maybe you can, yeah. So we will have heard of the term. So deep reinforcement learning basically uses, so it DRL. So basically it combines not just neural network, but deep neural network with reinforcement learning. So I'll explain from the perspective of the neural network. So suppose this is your state and this is the like number of actions, right? And maybe like in between you can have some hidden layers and some connections, right? And like it need not be fully connected, right? Neural networks can be sparsely connected also. So this is the input is your state. And for each action, suppose A1 action you have a node, A2 action you have a node, A3 action you have a node. So you will be giving actions like this state. So it's like state feature. Suppose I mentioned that you can have X coordinate as one feature, Y coordinate. Maybe you are working in 3D Z coordinate also, or some other feature time also, right? I think there is something in chat. Okay, right. Nothing. So what happens is like you need to map this state to this. Like suppose what is q value? So basically I told you before also, suppose this is state s. So q s of a1, you need to find this one value, and q s of a2 also you need to find, q s of a3 also you need to find. And then once you have like the q values of all three actions, you will take argmax and choose that action whichever gives you the highest q value. So in this way this works. So this is like basically outputting the q values of each action. So if we are in continuous space, like for discrete actions, we have like three actions here. So three nodes are fine. But suppose if we go to continuous space, then suppose if our actions is like between in 0 to 1 interval, and it's like all the real numbers. So it's infinite, right? We cannot be having infinite nodes for each, right? So they're like these value functions based approaches suffer a lot in continuous action spaces. So they're like we use policy gradient. Like policy gradient is either way, like they will be discussing in great detail in upcoming lectures. But policy gradient directly optimizes using policy. So policy is by like some mapping to either. So it tries to find directly the optimal policy, which will be pi star, without like worrying about what are the values. But how value function based approaches work is like you first find the value functions or q values, and then based on these q values, you will apply argmax and get the policy, right? So eventually, like you'll be getting one of these actions will have highest q value, and that will be your policy. Like this state will map to, suppose it's if it's a1. So this value function based approach is essentially two-step approach, and policy based is one step. It directly searches in the policy space. So policy based methods like work better in continuous spaces. So you need to figure it out on the basis of this discussion. What is the answer? Okay, so second last question for today. Let us assume some full RL problem. We are acting according to a policy pi. At some time t, we are in a state S where we took action A1. Okay, sometime t, we were in state this S and we took action A1. After few steps, like you wandered around in the MDP and you came back to the same state now at time t dash. And now you took what action? A2. And these are not equal to each other, right? Not equal. I'll write it this way. So this is not equal. Which of the following statements is true? Pi is definitely a stationary policy. Pi is definitely a non-stationary policy. Pi can be stationary or non-stationary. So can it happen that you have a stationary policy? Remember, it's talking about stationary, not deterministic or stochastic. This is different. Stationary means which doesn't change with time, right? And non-stationary means which changes with time. So what is happening? Suppose if we have a stochastic policy, maybe consider the general case. Either way, like deterministic. So stochastic policy, what happens is A1, A2, A3, suppose these actions are there, AK, and everyone will have some probability, right? And this will sum to 1. And in deterministic, what happens is similar setup, but only one of the action will have complete 1 probability, others will have 0. So this is deterministic problem, like deterministic policy. So deterministic basically becomes a special case of stochastic at extreme level. So we can consider stochastic policy. Now we have a stochastic policy. Suppose we have A1 with 0.4 probability, A2 with 0.6 probability in this state S. Now, what can happen? It is asking if we have a stationary, suppose if these probabilities are constant, these are not changing. Can it happen that at like both these steps we are choosing different? Yeah, like because it will depend on the random number which you are generating. If it's less than zero point 0.4, then we will be choosing A1. Suppose we are at time step t, we generated a random number and it's less than zero point 0.4. We will choose A1. If it's more than or equal to zero point 0.4, then we will be choosing A2. So it might happen that here like it comes greater than zero point 0.4 and it comes lesser than zero point 0.4 here. So we will be choosing different action. So it need not be a non-stationary policy, right? With a stationary policy, so this option says that it is definitely a non-stationary policy, but we are able to achieve this with stationary also. So this is definitely wrong. Now pi is definitely a stationary policy. So even if like suppose at time t this was the policy and time t dash maybe a1 a2 it became a1 became zero point 0.3 and this became 0.7. So still like we can have a1 and a2. So again like this is also incorrect. You can get the answer. Like it is possible that we can have two different actions in a non-stationary policy also. So it need not be definitely a stationary policy. It can be non-stationary also. So it can be both in fact. Okay, then I'll move to the last question. So the last question says that in solving a multi-armed bandit problem using the policy gradient method, are we assured of converging to the optimal solution? So I showed you this before also. Suppose we have this kind of function which we are maximizing over. So generally like we do it in an iterative manner, right? So sometimes what happens is we might get stuck in local optimum and it's hard to get out of this local optimum. So is like the convergence guaranteed that we will always reach this optimal? Need not be. We might sometimes get stuck in the local optima, and this is for gradient ascent, and you can similarly do for gradient descent also, like something functions like that. There we get trapped in local minima. Here it's local maxima. But the aim is to reach the global maximum. But sometimes we don't converge to the optimal solutions. So accordingly, you can get the answer. So I think like all the questions are done. So if there is any more doubt, like you can ask me in the chat or you can simply unmute yourself and ask me. Now I'll be referring to some reading materials. So basically, like last time, what happened is someone was asking to link this Saturn and Barto book. So I have linked it. Either way, like you can find it on the internet, just search it. So here, like chapter 2. So this is like basically bandits parts. You can read these. So 10 is summary of the entire chapter, and you can read point 8 and point 9. And this chapter 3 is the start of full RL. And the last two lectures, sir has already covered till 3.5. So it would be better you can read till section 3.5. Or if you want to be ahead, you can read beyond that also because chapter 3 is important. And till now, like bandits, I can understand maybe Saturn and Batu doesn't give that much focus to bandits. But from now on in the full RL part, you should follow the book religiously. So you should read this till 3.5. And again, like someone was asking about notes. So generally, like notes are person to person dependent. I, I have linked some notes on reinforced algorithm, might be useful to you, but I'm not sure like whether I'll be doing this for the upcoming topics also. If I am able to find, then I'll link because I'm also taking this like NPTEL course first time. So I don't have like contact with seniors or something who might have made notes. So generally the idea is like you guys prepare your own notes so that it varies from person to person. Suppose I might be I have taken an RL course in IIT Bombay, so I'm no I'm already familiar with some of the concepts, so I won't be writing those in notes, right? So but you guys might be needing those concepts in the notes. So it's good that you watch the videos and accordingly you prepare your notes like try to like it's kind of trade-off. If you like focus too much on preparing notes, then you won't be focusing much on understanding. But if you focus only on understanding, you might need to write some notes you might not write, and before exams you'll think like I forgot many things. So you need to prepare notes accordingly. Okay, so then I think that was it from me in this session, and thank you. If there is any more doubt, maybe I'll wait a couple of minutes and then I'll close the session. So in that time, you can ask me any doubt or something. Is there any doubt? Maybe I'll check in chat once. Okay, yeah, thank you. Okay, so again, like if there is no more doubt, then we will be meeting on same link and same time next Tuesday. So today is 13 and we will be meeting on 20. Okay, so I'm still here. So yeah, bye. If there is any doubt, anyone you can unmute and ask. Otherwise, like I'll be closing this session. Right. Oh yeah, I think like there is no doubt. So I'll stop sharing my screen. Now maybe like how many people? Like there are only okay. So maybe if you have doubt, you can ask. Otherwise, like I'll close this session. Maybe I'll stop the recording first.